nonlinear correlation. It is when the ratio between the two variables is not constant of change, or when the relationship between the two variables is plotted on the graph and all the points on the scatter plot tend to lie near a smooth curve, the correlation is nonlinear. I have here an example of curvilinear. On the x-axis, we have the performance, and on the y is the stimulation. So, as you can see, there is low, average, and high. At the same time, with on the y-axis also. So, it is the example of curvilinear. So, what is the difference of linear to nonlinear? On our previous reporter, it is also discussed the nonlinear. So it is said that correlation is said to be nonlinear if the ratio of change is not constant. In other words, when all the points in the scatter diagram tend to lie near the smooth curve, the correlation is said to be nonlinear or curvilinear. This is shown in the figure on the right. So this is the nonlinear correlation, y-axis and x-axis. So it is nonlinear because it is curve. And on the other side is the nonlinear. It is straight. Next, how to measure nonlinear correlation between multiple variables? The best known relationship between several variables is the linear one. This is the type of relationship that is measured by the classical correlation coefficient. The closer it is in absolute value to 1, the more the variables are linked by an exact linear relationship. So you can see the table, the linear relationship. Correlation between x and y is almost 90%. This is linear. Okay. As you can see, non-linear relationship. Okay. The correlation between x and y is almost zero. So from the y and x axis, so correlation is 3.0%. So it is curve because it is nonlinear. So when two variables hereafter x and y share information, provide information in a redundant manner, the amount of information provided by both variable x and y to predict z will be inferior to the sum of the amount of information provided by x to predict c and by y to predict z. So x, y, and z. So why it is called redundancy. Next is the complementary. The complementary relationship is the exact opposite situation. In the extreme case, x provides no information about z, neither does y. But the variable x and y together allow to predict perfectly the values taken by z. In such a case, the correlation between x and z is zero, as in the correlation between y and z. But the correlation between x and y and z is 100%. This complementarity relationship occurs in the case of nonlinear relationship. So we use this complementarity and redundancy in nonlinear correlation, and much then be taken into account in order to avoid any error when trying to reduce the dimensionality of a data analysis problem. Discarding x and y because they do not provide any information on z when considered independently would be a bad idea. Two possible measures. So I have here two possible measures of multivariate nonlinear correlation. First is the symmetric measure and asymmetric measure. The symmetric measure, the first one is a measure of the information shared by invariables B1 to Bn, known as dual total correlation among other names. So these measures of the information shared by different variables can be characterized as minus n to h V1 to Vn plus H, where H be expressed the entropy of variable V. That is the formula. When normalized by H is to V1 to Vn, this mutual information score takes values ranging from 0%, meaning that the n variable are not at all similar to 100%, meaning that the n variables are identical except for the labels. This measure is symmetric because the information shared by x and y is exactly the same as the information shared by y and x. So the Venn diagram above shows the variability or entropy of the variables B1, B2, and V3 with circles. The shaded area represent the entropy shared by the three variables. It is the dual total correlation. So next is the asymmetric measure. So from the variable x, the animal species, and y. So the symmetric property of usual correlation measurement is sometimes criticized. For example, if X takes another species and Y takes another families of values, for example, then X easily allow us to know Y, but Y gives little information about X. So in plain